Okay, so in this video, we're going to start finishing up the notes for the unit, and we're going to talk about something called angular momentum. Okay, so last semester we talked about linear momentum, and linear momentum, remember that's P, is just mass times velocity. But as we've seen as a common theme throughout this whole unit is everything we learned about previously, we can basically still have in rotational land as long as we make the appropriate changes. Okay, and so instead of mass, we learned in the last video that the rotational version of mass is I, where I is the moment of inertia. And then we learned in the unit 5a that instead of v, the rotational version of linear velocity is angular velocity. Okay, and so if you multiply those two things together, you get what we call angular velocity, and that has a capital L. Okay, I don't know why, but the symbol for not angular velocity, angular momentum, the symbol for angular momentum is a capital L. And again, I don't know why that is. Typically, you're given the information to find the moment of inertia and the angular velocity. If you ever had to calculate moment of inertia for a point mass and you did not have the angular velocity, but you only had the linear velocity, then you could also use this equation here. That's not super common, but just in case it ever shows up, I want you to make a note of that equation in your notes as well. Okay, so pause it there and make sure you get that down. Okay, so what can you do with angular momentum? Okay, so angular momentum is actually one of the most important concepts in the universe. This is just an overview slide telling you what L is, right? Moment of inertia times angular velocity. It tells you the units of everything. The units of angular momentum, they don't have a special name, but it's kilograms times meter squared divided by seconds. Okay, the reason for that is that's what you get if you multiply the units of I and omega. But I mainly want to talk more about the concept of angular momentum. Okay, and so there's not a lot of situations where you are just calculating angular momentum, but one of the key concepts in this unit is what's called conservation of angular momentum. Okay, and so we've actually seen conservation laws before in the past. We saw conservation of mechanical energy last semester. We saw conservation of linear momentum last semester. And basically the way any conservation law works is you have an initial value and a final value, and those two values are equal to each other. Okay, and so I'm just going to rewrite this even though it's on the screen in front of you. In other words, if you have a situation where conservation of angular momentum applies, then the initial angular momentum is equal to the final angular momentum. Okay, now you might be asking yourself the question, hopefully, in what situation is the angular momentum conserved? Okay, and what you see is up here on the top of the screen, it tells you the exact condition under which angular momentum is conserved. Angular momentum of an object is conserved if the net external torque is 0. Okay, so in other words, if there's no net torque in an object on I should say on a system, then the total angular momentum does not change. Okay, and so we'll see what that looks like, but basically what that means is that the initial angular momentum would be I initial times omega initial, and the final angular momentum would be I final times omega final. Okay, and so there's many interesting applications of this. One of the most common applications of this is when you see like skaters skate. Okay, and so if you ever watch like a skater or an ice skater skate, depending on how they adjust their body, they can actually change their moment of inertia, which changes their angular velocity. Okay, and so I will link some videos in so you can see what that looks like. But that is one of the key applications that we'll talk about in this unit as far as conservation of angular momentum goes. Okay, so what we'll do now is we'll just do a few calculation questions just so you understand how to solve problems with conservation of angular momentum. Okay, so make sure you get this equation down in your notes. Okay, so let's see how you might apply conservation of angular momentum. Okay, so here's an example. It says a merry-go-round rotates at the rate of 0.25 revolutions per second. Immediately before I do anything else, I see revolutions per second. This is omega, right? Revolutions per second is telling us how fast it's spinning around, but the SI unit for omega should be radians per second. So in my mind, I'm immediately thinking, okay, so I have omega, but I need to unit convert that before I do anything else, or before I go farther in the question. So there's a merry-go-round rotating. So this is omega for the merry-go-round. There's a 100-kilogram man standing at a point 2.1 meters from the axis of rotation. Okay, now because it doesn't say anything else, I think I can treat the man like a point mass. Okay, in which case his I is just going to be mr squared. The question is asking what is the new angular speed, okay, so the new omega, when the man walks to a point 0 meters from the center. Consider the merry-go-round as a solid 74 kilogram cylinder or a disk of radius 2.1 meters. Okay, so there's a lot going on here, so let me open up a new slide. And so this is a situation where we have conservation of angular momentum. Okay, and so let's take a look. Um, we have here, oops, I didn't mean to close that. Okay, so we have here the initial omega, okay, is 0.25 revolutions per second. Okay, so I'm going to write this down. I'm going to write down my givens. Okay, 0.25 revolutions per minute, or revolutions per second, which I'm not going to show the calculation because you should be able to do it at this point, but I need to convert that to radians per second. Okay, so 0.25, I know one revolution is 2 pi radians. Okay, so I multiply by 2 pi and I get 1.57 radians per second. That's going to be my omega I. Now the question is asking, what is the final angular velocity? Now you might be asking yourself, why would it change? Why would it spin faster or slower just because a man is walking? Okay, so what happens is as the man walks towards the center, the moment of inertia changes, and so the equation for conservation of angular momentum is we have I initial omega initial is equal to I final times omega final. Basically, what that means is it's going to spin faster or slower if the moment of inertia changes. Now, in this case, the initial moment of inertia, we have the disk and we have the man, and so the initial moment of inertia is just going to be the moment of inertia for the man plus the moment of inertia for the disk. Okay, now the man, let me write down his information. He has a mass of 100 and he's 2.1 meters from the axis of rotation. Okay, so the man has a mass of 100 kilograms. He has an initial radius of 2.1 meters from the axis of rotation. Okay, let me double check that. Yeah. And then he walks to a point 0 meters from the center. The merry-go-round, which is the disk, is a solid 74 kilograms with a radius of 2.1 meters. Okay, so for the merry-go-round, I have the mass. I'm going to write disk just because it's easier to write than merry-go-round. That's 74 kilograms, and the radius is 2.1 meters. Okay, so this is the initial moment of inertia. I have the man. Okay, the man is like a point mass. And I know for a point mass, the moment of inertia is just mr squared. For a disk, I look at my OnRamps formula sheet and I see that the equation is mr squared divided by 2. Okay, and so since I have all of these values, I can plug in to find the initial moment of inertia for the man. Okay, so that is going to be 100 times 2.1 squared plus 74 times 2.1 squared. Sorry, let me just make sure. Write that down. 2.1, 2.1. Yeah, and then divide by 2. And so the initial moment of inertia for the man, I have 100 times 2.1 squared plus 74 times 2.1 squared divided by 2. And I get 604.2 kilogram meters squared. And that is the initial moment of inertia of the man. Okay, now what is the final moment of inertia for the man? Well, it's the exact same calculation. It's the I for the man plus the I for the disk. But the difference is that when I go to do the mr squared for the man, his r value is now 0. Because if you go back and you read the question, he walks towards the center of the disk so that he ends up at the center of the disk. Okay, go back and read the question. The man walks to a point 0 meters from the center. Okay, so in other words, I have 100 times 0 squared plus 74 times 2.1 squared divided by 2. Okay, and so the new value of I is going to be 74 times 2.1 squared divided by 2, which is 163.2 kilogram meters squared. Because this whole thing goes to 0, so this gets killed off. So I have I initial, I have I final, I have omega initial. Okay, and so now all I have to do is take my equation for conservation of angular momentum, which I will do right here. I plug in my I initial, my omega initial, I plug in my I final, and then I just divide to get omega final. And I'm not going to write out all the numbers just because I have limited space, but I have I initial, omega initial, divided by I final, and I'm going to type all these numbers in. And what should happen is because the moment of inertia of the merry-go-round is actually going to get smaller, what should happen is actually the whole thing is going to spin faster. Okay, and so going back to the ice skater thing, um, when an ice skater wants to spin faster, if you go watch videos of ice skaters, what actually happens is when they pull their arms in towards their chest, they actually spin faster. Okay, and so the reason for that has to do with conservation of angular momentum. And then when they hold their arms out away from their body, they actually slow down. Okay, and so while I was talking about that, I finished doing this calculation and I get 5.81 radians per second. This is going to be the final angular speed of the merry-go-round. Okay, and so because the man walked towards the center of the disk, he decreased the moment of inertia for the disk, which made the whole thing spin faster. Okay, and so this is a conservation of angular momentum question. I would expect you to be able to do this level of question. I believe you have other similar questions on your quest homework, um, but this is the type of question that you definitely need to be able to do because it's a very common type of question to be asked. Okay, the way you spot a conservation of angular momentum question is usually if there's something to indicate the moment of inertia is changing, if they talk about more than one angular velocity, if it's like spinning faster or slower, a lot of the times that will indicate it is a conservation of angular momentum problem. Okay, and of course, if you see like a figure skater or an ice skater and it's talking about them spinning like faster or slower, that would be another context clue that it's a conservation of angular momentum question. Okay, so pause there if you need to look at the work for that question. Okay, and so the other questions that we will talk about in class, sorry, the other questions pertaining to conservation of angular momentum we'll talk about in class, but I will make sure to share the links with the ice skater video. And then another application of conservation of angular momentum is actually when stars get really really big, massive stars, of course, spin around on their axis, but when they die, they get a lot smaller because all of the mass gets blown away in a giant supernova. And so because they get smaller, what actually happens is those remaining stars actually end up spinning faster. And this is something that you might learn about if you ever take a class in astrophysics. But I will try to link a video to that as well, because that's another cool application of conservation of angular momentum. Okay, and so we're very close to being done with the notes for this unit. We will talk about Newton's second law for angular rotation, which involves torque, moment of inertia, and angular acceleration. And then we'll do a few more calculation questions with rotational kinetic energy, but by and large, we're done with the notes for this unit. Okay, so please check out the videos that I will link. The plan will be to finish the notes next time I see everybody in class, and then we will hopefully be prepared to take our exam next week. Okay, so as always, please let me know if you have any questions, and I will see you guys in the next video.